The goal of our video will be to demonstrate the equation of motion F equals ma with an off-axis and friction force. To accomplish our experiment, we will have two masses connected via this thread over the frictionless pulley. When released from rest, mass A will drop straight down, providing an off-axis tension force to mass B, which is our frictionless cart. It will then be pulled across the x-axis. To record the motion, we're going to be using a vernier motion detector to record our acceleration and our position, and data will be logged on the computer using Logger Pro.
This is the diagram of the apparatus that you just saw. We're going to be conducting a theoretical experiment here on the board with our equations to arrive at a theoretical value which we'll attempt to verify with an actual experiment that we'll conduct in just a moment. So we've set up our equations here. We have a diagram, free body diagram of our two blocks, a given, a find, and then our actual equations. So I'll run through how we went through this process. Our goal is to find the instantaneous acceleration of our block B when the block A is released from rest. So moving over to the diagram here, block B, we're determining the instantaneous acceleration of this right as block A is released from rest. So we have some values that were given. We've measured the block A, block B, their masses we have here. We're assuming that the mu, the coefficient of friction for our cart is 0, and then we measured the initial theta by getting a hypotenuse and an x component of our length. So moving on to our free body diagrams, we divide it into our block A and our block B, summing the forces. So the goal of this experiment was to use Newton's second equation of motion, or his second law, force equals mass times acceleration. As soon as A is released, we have to sum the forces in the specified direction and equal that not to 0, but to the mass times the acceleration. So beginning with block A, if we sum the forces in the y direction, we have the force of tension, and the weight. So sum of the forces in the y equals the mass times the acceleration of y. Plugging in those values here, we get two unknowns, the tension and the acceleration, because we're assuming that at the instant of the release, the acceleration of A equals the acceleration of B. So moving to block B, if we look at our free body diagram, we have the force of friction, the normal force, the weight, and the tension applied at a theta. We have our initial theta. So if we sum the forces in the x direction here, so the forces in the x equals the mass times the acceleration in the x, we have force of friction, the x component of the tension, and the mass and acceleration of the block B. Force of friction is equal to mu times our normal force. Since we're assuming for this component of the experiment that mu is equal to 0, with friction being equal to 0, the frictional force will go to 0, as you'll see here. We have our x component of the tension, our mass, our acceleration. So now we again come to two unknowns, our tension and our acceleration. We have now two equations with the same two unknowns. We can solve these equations as simultaneous equations in the calculator, arriving at our theoretical value of A, our instantaneous acceleration of the block B, equal to 0.697 meters per second squared.
Now we will collect the data and the acceleration when I release the cart from rest. From the moment we released the cart, the data was recorded in Logger Pro. The data is then automatically put in a chart showing acceleration over the position. This shows the acceleration over the entire run of the cart. Since we're only interested in the instantaneous acceleration, we're going to look at the beginning portion. Theoretically, our cart has 0 friction, but in real life we know there's a little bit of static friction. Take this into account, we took the average from rest to when it started moving, and we found the average acceleration. This was 0.737 meters per second squared, and that actual real life data compared to our theoretical calculation of 0.697 meters per second squared is only 5.7% error difference. demonstrate the effects of friction on acceleration, we looked up the coefficients of friction for paper on paper and set up the apparatus accordingly.
What you just saw, when we accounted for the force of friction using paper on paper, we repeated our calculations to arrive at a theoretical value for our acceleration for accounting for friction trial. So we did the same basic calculations as previously, but accounting for friction, so we have a value for mu of 0.28 for the paper on the paper. And the normal force is related to the y component of the tension and the weight. So following the same calculations as previously and changing the value of the mass A to overcome that new friction force, we arrived at an experimentally determined value of 1.58 meters per second squared for our instantaneous acceleration. And our experimental acceleration, we had a value of 1.68 meters per second squared, giving us a very reasonable percent error of only 6.33%. For this experiment, we had a few possible sources of error. We conducted 2 trials to relate how friction plays a part in the experiment. One where we assumed that the friction was none, and one where we accounted for the friction. In the trial where we assumed that friction was equal to 0, in the experiment, we did account for some static friction by using the average of that small portion of acceleration on the graph. But in the actual calculations on the board, we assumed that the static friction was equal to 0. So a possible source of error, that static friction actually has a tiny small value, so that's a possible source of error. Also, our calculation of theta, it was difficult to measure the length of the string with the apparatus and get the angle exactly right. It was very close, but that is one possible source of error. Also, the graph interpretation. We're very careful to use the portion of the graph that seemed to relate most closely to the instantaneous acceleration, which portion from the period of time when the block A was just released to when this actually starts to move. But overall, since we minimized the sources of error that we could control, our values for both the trial 1, where we did not account for friction, and trial 2, where we did account for friction, came out with very reasonable sources of error. So this experiment was designed to demonstrate the Newton's second equation of motion, second law, force equals mass times acceleration with off-axis tension force and the friction. Hope that you enjoyed how we showed those calculations in use.